All right, here are solutions to perfect problem 7 for Math 243. We're given these two different situations, and we want to do classical hypothesis testing and p-value hypothesis testing for both of them. So in this first one, we're talking about Michael Jordan and how much he scored during the playoffs. The key word here is that I suspect that his scoring differed. Maybe I'll underline that. It's our key to tell us that we'll be doing a two-tailed hypothesis test. His career scoring average in all games, just trying to give you a hint that that right there was our population average, which we use mu naught for, was 30.1, pretty impressive. In 179 playoff games, this is the size of our sample. Use the letter N to represent your sample size. He averaged 33.4. So sample average, we use X bar for the sample average. With the standard deviation of 15. Note that that standard deviation is talking about only in these 179 games. This is the sample standard deviation here. We use the letter S for this, not sigma, because it's not the population standard deviation. That's key. That's what tells us that we have to do a t-test here, not a z-test. And finally, we want to have 99% confidence. So that tells us that alpha is equal to 0.01. Alpha is always 1 minus your level of confidence. And with that information, I think we can start the problem. So maybe I'll go down here and split this thing in half. And on the left, we'll do this first problem. And we'll start out by doing it the classical way. And under the classical method, well, I guess under both methods, we're going to start by stating the null and alternative hypotheses. The alternative hypothesis is our claim. It's always mu. It's always describing mu relative to mu naught. Because we're talking about scoring differing here, we want does not equals in here. We want mu does not equal mu naught being 30.1 in this example. And you don't have to write this, but because our alternative hypothesis has does not equal in there, this is a two-tailed test. And our null hypothesis is always just going to be that mu equals mu naught. In this case, mu equals 30.1. So for the first one, we state our null and alternative hypotheses. Those are just these right here. The second part says to state the shape, the center, and the spread. Maybe I can do that off to the side a little. So what we want is the shape, the center, and the spread of the sampling distribution under the assumption that the null hypothesis is true. So our shape is approximately normal because it's going to have to be, because it's the only type of distribution we know how to study in this class. But we're also supposed to justify why the shape is what it is. And in this case, it's because n is greater than or equal to 30. That's the central limit theorem right there. Tells you that if n is greater than or equal to 30, our shape is approximately normal. And in this case, n was 179. Center of the distribution, it's given by mu naught, which is 30.1. The reason it's given by mu naught is because we assume our null hypothesis is true, and under the null hypothesis, we assume that mu equals mu naught. So mu naught becomes our center. And the spread, it's the standard deviation of the sampling distribution, is s divided by the square root of n. So in this problem, s was equal to 15. And n was some huge number, what, 179? So we can estimate that over here in our calculator. 15 divided by square root of 179. And you get about that, 1.12-ish. All right, shape, center, spread. Now we want to draw our picture. Looks like I got plenty of room here, so maybe I'll draw the picture. Well, conserve space. Draw it over here. So for our picture, we have this approximately normal distribution with center is 30.1. I'm going to draw this down here so I can make it bigger. This is kind of a key part of the problem. That's better. There's an approximately normal distribution. The center is 30.1, as I was told up here. The spread is 1.12. You can mark off standard deviations if you want. I usually don't. And then since we're doing the classical hypothesis testing method, what we have to do is figure out the rejection region. kind of following the steps here. So we know that the total error of our rejection region will be alpha, which is 0.01. But since it's a two-tailed test, that means we kind of have to split our alpha up into two different sections and have half of it over here, in other words 0.005, and half of it over here, 0.005. And we're going to figure out these critical values. We're going to get the z-scores for them, because our test statistic will be a t-statistic. And so we won't want to have the x values, this 30.1, we'll want to have the z values, so we'll have 30 in the middle. And now we've got to figure out these values. There's a few different ways to do that. You can do that on your calculator if you have the inverse t function. If you hit second and then distributions and you have inverse t in here, you can use that. Just put in 0.995, comma, and then however many degrees of freedom you have, which is always 1 less than n. So you could figure out this value down here by using inverse t, comma, 0.995, comma, 178. But I don't have that on this calculator. This is an older version. So there's a few different options. You could program it, as there's a video on my website showing you how to do so. Or you could go back to your tables. If we go to our tables here, our z table, it's a little bit hard to see. But this row right here is when you have 0.005 probability in that tail. And so my degrees of freedom were 179. I think it was 178. There's no 178 in here. So we have the choice of using either 100 or 1,000. It really doesn't matter. You'll see these choices are really close together. I'd probably choose the 100 one, the 2.626. Because 178 is closer to 100, but different books will have different ways you handle that. Anyways, our critical value is 2.626, so I can label that down here. And if this one is 2.626, then this one has to be negative 2.626, because I'm down here on the z statistic row, and so we have that symmetry. So now all we got to do is figure out our test statistic, and if it's in the rejection region, we reject the null hypothesis. And the way you can do that is you hit the stat button on your calculator, and then go over to tests, and then down to t-tests. It's important that this is a t-test, not a z-test. We have data, mu naught is equal to 30.1. Oh, sorry, we don't have data. We have statistics about the data. We don't have a list of data itself. We have statistics about the data. Mu naught is 30.1. X bar was 33 something, 33.4. S, so I'm not asking for the spread here. I'm asking for S, which is 15. And N, not asking for the degrees of freedom. I'm asking for N, which is 179. And then you tell it your alternative hypothesis is this one, that mu does not equal mu naught. And you go to calculate. And what it tells you is that our test statistic is 2.94. In other words, somewhere out here, we have this value of 2.94, which corresponds with 33.4 points per game. And this point is in the rejection region. If I made this a little bit longer, we could have seen it better. This test statistic in green is in the rejection region in red. So our conclusion will be, maybe I can start up here, because the test statistic, which was 2.94, is in the rejection region. There is sufficient evidence to reject the null hypothesis. And conclude that, let's see, in this problem we said being in the playoffs, oh, sorry, that's the second one. Being in the playoffs affected Jordan's scoring. Conclude that being in playoffs affected Jordan's scoring. And now I still have to do this the p-value method way. The good news is that there's not a whole lot of extra work to do. This is classical up here. This is p-value down here. Picture's going to look somewhat similar. I'm going to start by drawing a distribution that's approximately normal. Good enough. And in the middle I have 30.1, which corresponds with the test statistic of 0. And then if I go over here, I have a p-value of 0.003 that corresponds with this test statistic of 2.94. So way over here, when he scored 33.4 points per game and there's a test statistic of 2.94, the p-value, this is my p-value down here, is equal to 0.0037. So my conclusion is, because the I don't know where to write this. Okay, maybe over here in blue. Because the p-value is less than alpha. My p-value is 0.0037, alpha is 0.01. Because the p-value is less than alpha, and then jump down here, there is sufficient evidence to reject the null hypothesis. Maybe I'll put ... Good enough. And conclude that being in the playoffs affected Jordan's scoring. Good enough. There's the first one. Second one here. Maybe I'll do the second one in a different video because this is already getting pretty long. So I'll end this here and make another one for p-value or for proportion hypothesis testing.